Hi everybody, my name is Gabi Nakibly, and today I will be talking about a large-scale internet survey in which we discovered or investigated the practice of forced content injection by network operators. My collaborators are Jaime Schcolnik and Yossi Rubin. It is well known that some network operators alter their users' traffic. Actually, over the past few years, there have been several such occurrences in which users spotted their ISPs doing so, mainly to inject advertisement. And indeed, there were some excellent papers that studied this practice. All of them actually use the same method in order to detect content alterations. They simply set up a web server and with a specific web content, and then they solicited many clients to fetch that content, and then an agent on the client, usually just a JavaScript delivered by the web server itself, compared the content displayed to the user to the content that was actually delivered by the server itself. And if there is a mismatch, then there is content alteration that is sometimes done by the network operator. Now, this is a great method to discover many content alterations for many clients in diverse geographies. However, it has one caveat. All clients fetch the same web content. So this tends to reveal content alterations by ISPs that are usually oblivious to the content they alter. And these ISPs tend to be edge ISPs, meaning the ISPs that are closest to the users, which mainly target their own customers and generally indeed oblivious to the content they alter. They just alter the content of all the web traffic of their customers. So indeed, all those works revealed content alterations by edge ISPs. In contrast, this is how we detected content alterations. We simply monitored the web traffic of many clients that resides in a handful of networks. This allowed us to monitor web traffic coming in from many web servers with diverse content. And this actually allowed us to detect content alteration for specific websites. Such content alterations simply cannot be detected in the previous method. And indeed, such content alterations are done by non-edge ISPs, which resides much closer to the website. So let me just illustrate this for you. So let's say on the right we have here a web server, on the left some users that are serviced by several different edge ISPs. So previous works discovered that there are edge ISPs that alter the user's traffic, and actually these alterations affect only their direct customers, and all the other users are unaffected, of course. In this work, we discovered that also non-edge ISPs alter user content, and since they reside much closer to the web server, then potentially all internet users are affected by these content alterations. So how exactly did we discover those content alterations? We simply leveraged the insight that network operators like to alter their content in an out-of-band manner. And before I discuss what is an out-of-band, let me just recap what is an in-band content alteration. This is simply using a middle box that sits in path and receives traffic, update the packets as necessary, and forwards the traffic to the client. Now, network operators don't like to do that because first, this middle box presents a single point of failure. If the logic in this middle box somehow fails due to a bug or something else, then the whole production traffic fails or stops. If this middle box becomes too loaded, then the production traffic slows down. And generally, network operators don't like single point of failures or performance bottlenecks in their network. So they try to minimize that as much as possible. So this is why they prefer doing an out-of-band content injection, which is simply placing a tap or a port mirror in line, and which copies the whole production traffic to an injector, which decides when to send the forged packet. The forged packet is simply sent as if it was a legitimate part of the TCP connection. And of course, as we've seen in the last presentation, this forged packet has to have the same source and destination IP addresses and source and destination TCP ports as the legitimate packets of the TCP session. And in addition, the forged packet has to have the same TCP sequence number as that of the legitimate packet it tries to forge. Now, notice that, of course, the valid packet is not dropped. So this means that the client receives two packets with the same TCP sequence number. So we have here actually a race between the packets. The first packet that arrives to the client wins the race and actually gets processed by the TCP stack, and its bytes, its payload is delivered to the web browser. The second packet simply loses the race, and it is discarded as an unnecessary retransmission. Okay, and this is actually what we search for, this kind of races in our study. We specifically just try to identify cases in which there are two packets in the same TCP session, having the same exact TCP sequence number, but carry a different payload. Now, the fact that they carry a different payload should not happen in a normal progression of a TCP session, and it is very indicative of a third party simply injecting a forged packet. Now, actually, out-of-band injection is not new at all as a technique. We already know that ISPs try to throttle peer-to-peer peer-to-peer traffic on their network using injection of TCP resets. We know that the NSA does TCP injection attacks to compromise the client. They call it the quantum operation. And we also know that censorship is done sometimes using out-of-band injection. Actually, throughout our study, we did encounter numerous incidents of censorship-related injections. We do not report on them. We report on these incidents in our paper, but we did encounter them. And actually, censorship-related injections aim to block traffic and are politically motivated, while in our work, we try to study injections which try to alter the traffic, not just block it, and are financially motivated. So these are the networks we monitored. In total, we monitored the 3 networks that service more than 75,000 users. And in total, we monitored more than 1.5 petabits of web traffic. And this is the table that summarizes all the injections we have found. We divided them into 14 groups based on the injected resource. Here you can see in this column the destination site, which is actually the site, the content of which was altered by the injection, the location of the site or the web server. As you can see here, many web servers are located in China. So this gives the first clue that the injectors are located also in China. The injected resource and the purpose of the injections. Out of the 14, 8 injection groups were aimed to inject advertisement, presumably to increase the revenue of the network operator. Surprisingly, 4 of the injection groups were malicious injections, which were aimed to compromise the client. And the 2 injection groups aimed to block content. However, we do not think they are censorship related. As an example, just to clarify what is exactly an injection, here's an example of an advertisement injection. And here you can see an HTTP request made to a resource at cnzz.com. The user originally browsed the site tfkp.com. And in response to that request, the user got 2 HTTP responses. The left one is the valid response, which is simply JavaScript code. And the right one is the injected response, which is a 302 redirection to another JavaScript in a different domain that simply redirected the user through a series of affiliate ad networks until it reaches Google's ad network. And there, of course, the user is served with an advertisement, and we assume that the injector benefits from this advertisement in some way. Okay, next we tried to reproduce the injection after the initial monitoring and analysis. So first I will note that all the injection groups were only observed for just a short period of time, just a day or 2 or 3, nothing more. After which injections of the same group were not observed again. So when we try to reproduce those injections, we simply try to resend the HTTP request that originally triggered the TCP injection, the injection we observed. And after we've done that, we were not able to reproduce any of the injections, absolutely none of them, which was a big disappointment. However, following our initial publication, another researcher tried to reproduce the injection, and he was successful, and he succeeded to reproduce 2 of the injection groups out of the 14. But then again, just for a short period of time, afterwards, the injections went away. And all this leads us to the conclusion that perhaps those kind of injections are transient in nature, and perhaps the injector targets a certain website just for a day or 2 before it moves on to other websites, presumably in order to stay under the radar. Now, as a side note, I will tell you that the censorship-related injections we encountered, which again we do not report on them in this paper, were 100% reproducible and very much persistent. So, who are the entities behind those injections? So we first try to identify the actual entities that inject, the actual injectors. However, we quickly realized that it is a very hard task because there is little identifying evidence behind those in the injected content. So instead, what we try to do is try to identify the location of the injector, or more specifically, locate the network from which the injected packet was triggered, or more specifically, locate the autonomous system from which the injected packet was triggered. If we identify the autonomous system, then we can identify the entity that is responsible to the autonomous system, and actually we can identify the entity that not necessarily is responsible to the injection itself, but at least responsible to the network infrastructure from which the packet is, the injected packet is triggered. So now bear in mind that we were not able to reproduce the injections, so we could not simply send the HTTP request that triggered that originally triggered the injections over and over again with increasing values of TTS until we get back the injection. So we had to resort to a different heuristic, which simply leveraged the TTL value in the injected packet. So for this, we leveraged the insight that there are common initial TTL values set by major operating system, which are 32, 64, 128, and 255. There are other values, but these are the most common ones. And we actually use that values in order to calculate how many hops the injected packet traversed. So if, for example, we observe an injected packet with a TTL value that equals 59, then most likely the initial TTL value of that packet was 64. Then we can estimate that the packet may have traversed 5 hops. So if we actually know the path from the server to the client, and we assume that the injected packet was indeed triggered from along that path, so we can actually estimate the location of the injector by simply counting 5 hops from the client back to towards the server. Now, it doesn't really have to be very accurate because we don't really need to pinpoint the exact location of the injector. We just want to identify the autonomous system of the injector, so it doesn't have to be quite accurate. And these are the analysis the results of our analysis. Here you can see which were actually quite consistent. In all cases, in all cases, the injector, according to the analysis, resided 2 to 5 hops away from the targeted web server. And that meant that in all cases, actually the injector resided within the autonomous system of the targeted web server, which is kind of plausible because indeed when you try to alter the content of some web server, of some website, you want to be as close to it as possible. So these are all the numbers of the autonomous systems. And on the bottom table, you can see here the names of the operators which are responsible to those autonomous systems. And here you can see that indeed China Unicom and China Telecom are responsible for most of the injection. And again, we are not sure that they are the ones that injected the forged packets, but they are responsible from the network infrastructure from which the injected packet was sent. And we know that the injector had access to the network infrastructure. Actually, for the American ISP, we know that it was not directly responsible for the injection because it was a victim of an attack which the attacker simply compromised one of its routers, and then the attacker used this compromised router in order to attack other users, in this case, a gambling site. Okay, so to conclude, following a large-scale survey of internet traffic, we discovered that not only edge ISPs practice false content injection, but also non-edge ISPs, mainly Chinese ISPs, and they actually affect all internet users, not only their customers. And we also discovered numerous incidents of malicious attacks. And we also, in the paper, I don't discuss it here, but in the paper, we also discuss proposed mitigation proposed client-side mitigation that blocks those injections, assuming that the client cannot access the site using an HTTPS. And we also publish samples of those injections, representative samples of each injection groups. So you're very welcome to dig in and look at these injections. And that is it. Thank you very much.
Hi, Ben Stock, Saarland University. About the identities of these injectors, did you also see cases where the TTL was actually matching what you would expect from the actual host?
Yes, so actually the injector could, in fact, I don't know if it easily, but it can indeed match the TTL. In fact, in all the injected packets we found, the TTL and the identification fields do not match the legitimate packets of the TCP session. They can, in principle, do that, but they do not bother doing it because probably no one ever looked, or I don't know. But it is possible, but they don't do it. Actually, we did find some cases in which the injector perhaps tried to do it. For example, we found out that it's not the TTL, the identification field in the IP header was identical to the identification field of a legitimate packet sent by the server, but the bytes were switched. Probably the injector had a big little Indian bug there. So, but other than that, currently the injector we observed did not try to mimic the TTL and IPID values.
Okay, thanks.
Hi, Stefan Savage, UC San Diego. Very interesting stuff. There's something that feels off, and I'm just wondering if you can help me think it through. So we know about off-path stuff for censorship. That's been around for a while. And in-path ad injection they're companies who sell the equipment. What you're demonstrating is potentially out-of-path ad injection as the primary motivation, as you said, for financial benefit. But the fact that that you see so few of these and that they're not replicated suggests that, in fact, the financial motive is unlikely to be what's going on, because you don't make a lot of money by putting a half dozen ads out there and building this complex infrastructure and then not using it.
We're not able to reproduce those specific injections for those specific websites. We assume, we do not really know, but we assume that the injector do not target only those websites we found, but perhaps it targets many other websites we simply have not found.
So I want to put out one other theory for you to consider, and that is that, in fact, there is an in-band injector. These are not typically the best written pieces of code, and what you are witnessing is an in-band injector having a brain fart and sending the original packet and the modified packet occasionally, which seems like it would also produce your same results.
So who actually sends you said the malicious software on the server side?
The injector is an in-band device that is meant to inject ads, and it's supposed to not send the original packet and only put in the injected packet, but it screws up. And sometimes it sends the original packet too.
Okay, so you're actually saying that it might be a network operator with faulty...
Absolutely. We have network operators that do in-band injection. It already exists.
Okay, so this is actually what I'm saying, that network operators inject forged packets in order to inject advertisement into their users. Okay, so I'm saying the same thing as you're saying, or I'm missing something. Network operators indeed inject advertisement.
But that's an established fact, right? We have other papers demonstrating that. Mm-hmm. But the out-of-band thing is very new and elaborate, because it's potentially not the ISP of the person who could be doing it. That's what makes it fascinating, that it's someone who is not the person who owns the end site who could be doing this.
Still out-of-band injection requires access to the network infrastructure, right?
Yes.
You need Okay.
True. All right. Well,
okay.
We can talk more offline. Just,
okay.
Yeah.
Thank you.
Any more questions? Okay. Thank you.
Thank you very much.